Hello, and welcome to the third session of the Specific Learning Disability Math webinar series, Let's Be Rational, Learning Integers, Fractions, and Decimals. Thank you for joining us. My name is Jill Marshall, and I am the Specific Learning Disability Specialist in the Exceptional Student Services Unit of the Colorado Department of Education. We are pleased to be sponsoring this webinar series, which focuses on helping K-12 educators develop effective instructional strategies to promote math success for struggling learners, including those with specific learning disability.
CDE is a dynamic service agency that strives to ensure all students in Colorado will become educated and productive citizens, capable of succeeding in society, the workforce, and life. To accomplish this vision, the CDE's mission is to ensure that all students are prepared for this success by providing excellent leadership, service, and support to schools, districts, and communities across the state. One way the CDE is committed to ensuring the success of students is to provide leaders and educators professional learning opportunities to support instruction in literacy and numeracy. This webinar series focuses on instructional strategies for teachers of mathematics. This slide reviews the SLD Math webinar series dates and topics that will be covered during each of the 5 one-hour webinars. Participants may register for any or all of the webinars. Please visit the SLD website for registration information and to learn about other professional development opportunities. The website link is provided at the bottom of this page.
Before I introduce our speaker, I would quickly like to review some housekeeping issues and information about today's webinar. This is a recorded webinar, and your microphones will not be activated during the webinar. Please sign into the chat box with your name, role, administrative unit or agency, and the grade levels you serve. Please type any questions you may have into the question and answer window or chat box, and we will address them as we are able during the presentation or at the end of the session. If you have difficulty accessing the webinar or have technical issues, please call Amanda Timmerman at 303-866-6969 or email her at timmerman_a@cde.state.co.us or contact Jill Marshall at marshall_j@cde.state.co.us. Please also feel free to email us after the webinar with any additional questions you may have.
There will be a brief event evaluation survey at the end of this webinar. The link will be provided on the last slide of this presentation. After you complete the evaluation survey, your certificate of attendance for one CDE training hour will open automatically. Please print your certificate for your records. The recording of this webinar will be made available to participants in the future. Please contact me, Jill Marshall, or Amanda Timmerman for viewing requests. And now I have the pleasure of introducing our presenter, Dr. Brad Witzel. Dr. Witzel is an award-winning teacher, professor, author, and professional developer. He has delivered over 400 international, national, state, district, and school presentations, as well as a dozen educational videos. Dr. Witzel has authored 9 books, 8 book chapters, and over 30 research and practitioner articles. He is a governing board member of the Southeast Regional Educational Laboratory, funded by the Institute of Education Sciences, and a member of multiple state-level MTSS and RTI governing boards. Dr. Witzel serves as the editor of Focus on Inclusive Education through the Association of Childhood Education International, and served as an author and panelist on the IES Practice Guide, assisting students struggling with mathematics, and as an invited reviewer with the National Mathematics Advisory Panel. Most importantly, he is a father of 2, husband of an educator, and son of 2 educators. I'm honored to be able to work with Dr. Witzel and to welcome him back to Colorado for the SLD Math webinar series. Dr. Witzel, welcome, and thank you for joining us.
Hello and welcome. This is Dr. Brad Witzel from Winthrop University in South Carolina. Today we're covering Let's Be Rational, learning integers, fractions, and decimals. To start us out, we've got to have a joke. So the child's writing the equivalent fractions on the board and he turns to his teacher and he says, "I understand they all have the same value, but I have to tell you, the ones on the right feel like more bang for the buck." Of course, they're all the same value, but kids do make that mistake quite frequently, right? The larger the number means the bigger the fraction. So what we're talking about here is it's one thing to be able to do the procedures, but we've also got to teach to the concepts. So let's talk about this series. We started in February focusing on the non-strategic learner. We discussed students' attention, executive functioning. We discussed students' working memory and how that affects their learning. And then we discussed what to do about those issues. That took us into a quick introduction to number sets and establishing understanding of magnitude of number and place value building, along with recognition of numerals. We carried that into March, where we discussed whole number operations, building from accuracy to fluency and to the dreaded automaticity. This time, we're focusing on rational numbers. We're going to discuss integers, fractions, and decimals. And just a warning, there's so much information in each one of these sessions. This one in particular, we could spend days just on the strategies for rational numbers. So a lot of this may be a quick introduction. We're then going to build into mathematics as a language coming in May. We'll discuss word problem solving and vocabulary building and trying to build a consistent effort from one year to the next. Finally, one of my favorite parts, we'll build into what are we doing with all this to set us up for an understanding of algebra. So we're going to discuss the progressions, the scope and sequence, what to do early so that it carries through later on. So let's discuss our framework we've been working with. We're working with the framework I wrote with Mary Little. We'll be working today, we'll use some of the strategies that come from the Teaching Elementary Mathematics to Struggling Students. We'll also be working on the Bridging the Arithmetic to Algebra Gap book. And together, we have a lot of different strategies that work directly when it comes to rational numbers. We're going to discuss instructional ideas in here. We're going to get very specific on strategies. And we're going to relate these strategies of how they work for certain students based on their learning characteristics. That being said, some things today will be based for core instruction, and other things will be specifically on what an intervention could be. So, here's the agenda. We're going to start out with frequent errors. First, errors happen. We're going to have to figure out ways around them, just like the child in the GIF. We're going to have to figure out what do we do with these errors. Because if you don't understand those errors, it's hard to know where to change your instruction. Not just at the core level, but understanding those errors help you gear the intervention. We're then going to show some modeling of decimals. We'll get into core instruction for decimals, and we're going to hint at some of the interventions later on. We're then going to focus on number line and the linear models, or the measurement models that some people like to call it. We'll then get into, real quickly, we'll talk about integer computation. We already hinted at it earlier on, of that negatives are just part of the number line that we need to do, but we'll get a little more specific on interventions today. And then finally, one of my favorite ones out there that's been popping up a lot in the research is on fractions using a multisensory math approach. And there's an intervention that I wrote a couple years back with Dr. Paul Riccomini that's gained a lot of traction in recent research. So I want to make sure we at least show that here. So let's start out before I start sharing research and boring you. It says, all right, what's more important, concepts or procedures? So if you have the opportunity and you're watching this in a recorded session, make sure that you hit pause here and discuss what's the most important, concepts or procedures. We always hear about one thing. What is the answer? Right? And I hope you read the cartoon because it's a good one. Only a math geek like me would really like that, I think. So let's get to the research. Bailey and his colleagues were studying students in China versus the United States in 6th and 8th grade. And what's really interesting about China and the United States, we all have our conceptions of what we think are happening, but the truth is we actually introduce fractions about the exact same age and grade levels as China. So they're trying to figure out Is it procedural or is it conceptual understanding? Which ones would China do better on? Which ones the United States do better on? And Bailey and his colleagues, even the colleagues from China who assisted on this, they actually assumed that procedurally, which is a Chinese focus, is to really hone in on the procedures to fractions. They figured they would be better at procedures. They also have a stronger arithmetic foundation than we do, typically, and most international studies. But we figured that conceptually, we got to be a little bit closer. Well, the results did not show that. The results showed that, particularly for the lowest achievers, the ones we're focused on here, the low achievers who had better understandings of fractions magnitude, that helped build the procedural knowledge. And then in turn, students who had the best procedural knowledge end up having the best conceptual knowledge. Just like we hinted at in the previous cartoon, and as you saw earlier on in the introduction, try not to separate procedures and concepts whenever possible. There are many times that our textbooks are littered with great conceptual understandings where a student gets to figure out what's going on there. We cut up pizza pies for them. But what we're finding is those conceptual ideas don't actually tie directly into the procedure. However, the procedural understanding, if taught correctly, without tricks, ties directly into concepts. So I'm going to make sure we explain that a little bit later on because that may not be as clear as I would hope it would sound. So let's do that. How do we convert this? Now, it's often stated that we're converting a mixed fraction to an improper, but I got to tell you, there's nothing improper about saying 4 2/5. So, and there's certainly nothing improper about saying 22/5, right? It's just, in some states, it's called a fraction with a larger numerator than denominator. But how do we do it? What do you do for this one? Well, do you take a 4 times 5 and make 20? Then you added 2. That gives you 22, right? And then that 5 just slides right on over to make it 22/5. And then when you're trying to teach it to students, you're trying to teach that pattern to them and they're getting confused. So you learn, I better draw some arrows to help remind them, right? So, and even sometimes we'll even put in some of these little indicators in here, like you'll put a multiplication sign here and you'll put an addition sign here and you'll force order of operations, right? But it's all forcing this procedural approach that's not connected to concept. So I ask you, why in the world does that multiply then add thing really work? Well, some of you already know this, but some, I hope that this is, when I learned this first couple years back, I was floored as to the why it works. So first, let's say the fraction. 4 2/5. When we have a mathematics language discussion later on, we'll get further into this, but and means two different things typically in mathematics. One, it means addition, right? But the other one, it means decimal. In this case, it means both. So what does it mean to say 4 2/5? Well, I'm going to make an addition problem right now. I want to make it 4 2/5. So I set up as a fraction, rather than just 4 2/5, I put 4 in the numerator, 1 in the denominator, plus 2/5. Well, adding ones and fifths is a little more complex than that. Let's get like denominators to make sense out of it. So I multiply both numerator and denominator by 5 each, right? Or multiplying by 1. So 4 times 5 in the numerator, 1 times 5 in the denominator. What do I have? You got it. That's where over here you have 20/5. That's the multiply 4 times 5. Then the denominator is now set. Once the denominator is set, that will be the answer. I usually consider the denominator like a base of a number. So now the answer is going to be in fifths. We're discussing fifths, the answer is going to be in fifths. So what does that mean for the numerator? Well, it means I'm talking about 20/5 plus 2/5. So the answer, 22/5. So why do we multiply, then add, and the 5 slides over? What you're really doing is just adding fractions with unlike denominators. Wouldn't it make more sense just to teach that to students straight up front? Let's do another one here. Let's try division of fractions. We've all read this, right? Invert and multiply. And I've got students here that think when you divide, numbers get smaller. But wait a second, it blows my mind. When I divide fractions, that answer keeps getting larger. I don't get it. So finally we said, well, just invert and multiply. I was even reading a book one time that said, it's not for you to ask why, it's for you to invert and multiply. Well, yikes, right? So let's make sense out of it. Why does invert and multiply work? Well, it's based on the principle of identity. In this case, I'm going to set it up as a fraction of 2/3 divided by 1/4. Wouldn't it make it a lot easier if I could just look at one fraction as my answer rather than two? Well, what do? Well, multiply by its reciprocal. But if I can't just do that, but I can always multiply by 1. So look, 4 divided by 4, that equals 1. So I multiply the numerator by 4 and the denominator by 4. What happens in the denominator? Well, that becomes, right, 1 times 4 and 4 times 1. Becomes 4/4, which becomes 1. Look at the numerator. The numerator, that's invert and multiply. So why do we say invert and multiply? Well, it's not that it's wrong to say invert and multiply. You're just skipping half the computation that needs to go into this problem. So I would suggest, rather than attacking division and fractions as a quick trick, focus on what's really happening and try to reteach the identity principle so our students understand what to do with it later on. Now, I know what everybody's saying, right? They say, oh, why did I teach? That's a lot to memorize. Well, yeah, it is, but I mean, otherwise, I've got the best 5th and 6th grade scores for kids who are probably going to fail algebra. So we've got to set up the fractions instruction so they can do well at algebra later on. This worked with this was sent to me by a teacher after a workshop who tried copying over some of the students' works and just labeled it for me of what's happening with their students. With this first part here, we've got 3 and 2x squareds, right? That'd be like 4 and 1/2. So I'm going to take this mixed fraction and we're going to convert it to what she wrote in here as an improper, or right, a fraction with a larger numerator than denominator. But the truth of the matter is it's really just trying to convert a fraction. So once I do that, look, it's that same setup. Same thing as you see working across. But look what also happens here. I've also have a division of fractions here in this algebra class. So instead of just invert and multiply, flipping up here, the teacher wants to see you know the principles behind it. So she's checking your understanding of the identity. And look, the student ends up having this complex mathematics behind it. I know what you're saying. Oh my gosh, I don't have a clue what I'm seeing up there, right? High school people are all like, yeah, I get it. Middle school people, yeah, but if you're in elementary, you don't have to work with polynomials much. Even if you understand the mathematics behind it, you're just not as familiar with it sometimes. Well, if you look at this, if I take out those x's and put in another number, I have a 5th or 6th grade math problem. But because the way it's designed, it becomes algebra. That's when we get to the arithmetic to algebra gap. It's how we set it up early that helps the student succeed later on. This picture is a little fuzzier, so I apologize for that. But this was sent to me by a group of teachers in Detroit after doing some workshops in Detroit. Same thing we just discussed here. Take a look at this. Mixed fraction, 5 and 1y, divided by 3 and 2y squared. So first they had to convert the fractions. Then they set it up, right? They combine that denominator. And now they have to do an invert and multiply. Nope, not invert and multiply, a true division of fractions with the identity principle. And this one, the student in down here wrote a 1 on it. So you get to see, again, it looks complex, and this is the distributive property that takes it from this step down to here. This looks complex, but the bottom line is the complexity that you see within here was handled early by a set of really good teachers who helped that kid succeed later on. Oh, trust me, as high school people, we know it. We get the credit for the kid learning this when the truth of the matter is this kid came to me prepped, ready to learn this. So what's the big deal here? Why are we pushing all this? Because I can get kids to learn that earlier. I get it. So Siegler out of Carnegie Mellon has done several different studies. He was even on the one with Bailey earlier. And he worked on what is the predictability of algebra. And what did it come out to? You got it. Understanding and computation of fractions. They called it facility of fraction. But it's computation and understanding of fractions and division. And if you worked with us back in March, you got to see how that division ended up coming through as well. It's an introduction of fraction. So fractions and division were the best predictors of algebra. And that is when you account for parents' education, income, gender, IQ, age, reading comp, working memory, right, and computation. You take those into account because we know those are important factors. What are we left with? Fractions and long division. So why is fractions such a big deal? Well, first, And the congressional panel, the National Math Panel, concluded almost a decade ago that difficulty with fractions is pervasive and is one of our biggest obstacles for furthering mathematics in this country. And they even predicted some of Siegler's work, saying, you know what, in order to succeed in algebra and beyond, you're going to have to be able to understand fractions, ratios, decimals, and percents. Well, Tom Lovelace, who does a lot of writing on mathematics, more on the casual end with his research analyses and explanations, which is always a good read. He's a great writer. But he wrote in there that students simply don't know how to translate fractions into decimals, and they certainly can't work with fractions on a number line. Well, you know what we'll be tackling later. So got some research closer to me that's getting a little old and I need to update. In fact, my friend Paul Riccometti's already begun to update this. But we're talking about the different students who enter algebra. The students who enter algebra on kind of in this state, it was called Math Tech, which meant like the alternate algebra programs. And this is the traditional algebra programs. We gave these students the algebra readiness test. And how do they do on the algebra readiness test when they're in algebra? Well, look at the details here. Fractions was a low, for students who struggled, fractions was just awful. But even students who were supposed to be high achieving, not even half of them could do the fractions in order to be successful in algebra, which meant the average student is not prepared for algebra for fractions. Decimals did a little better than that, and integers did a little bit better than that. But the bottom line is, rational numbers really stood out as some of our major error patterns in getting kids ready for algebra and beyond. Well, I don't want to belabor the point. You can always go over this on your own time. But students in the lowest achievement groups really struggle with computations. The ones that students did in the lowest group better than the other groups? Well, better relatively to their own work? Multiplication of fractions. Well, why? Very little conceptual understanding, right? It's numerator times numerator equals an answer. Denominator times denominator equals an answer. They actually did better even than the middle achieving groups in mathematics. But take a look at these scores. Students really struggled with fractions. The ones they did a little bit better with is when they are adding or subtracting fractions with like denominators. Start changing denominators, we start really having problems in there. So, Sabella Beckman, a friend of mine at University of Georgia, a mathematician, has done some work, and she's talking about what are some of the common errors here. She says, start with these length-based models, but students will look at them as ratio immediately. At the core level, we've got to start with a whole, not a one, but a whole. And you can tell that she's already working with fraction strips here, right? Little strips of paper have been cut up. She says, cut them into fifths so students see that relationship with each other. Some other people I get to work with a lot. Tim Burst out of University of Michigan's done some work. And look at these common errors we see here. For the top one, 34 hundredths is greater than 5/10. Well, why would that be? Well, right, the longer the decimal, right, they think it's got to be bigger. 34 is bigger than 5, right, so they don't really understand the place value behind it. Well, here's the ugliness. Once they start understanding, some of the place value behind it, we're trying to explain that it isn't always that way. Then they start looking at, well, which one makes more sense? Well, I understand what that 0.75 means. It's 75 hundredths, but I don't know what this 75,000,002 means, right? When you're starting talking about 10 millionths, the student starts getting thrown off, and so the student just assumes it can't be any bigger. Next thing through, we're just adding zeros, right? 20 is 10 times bigger than 2. So they assume these zeros in the decimals, right? They must mean something. And the last part, we've even seen this working through with undergraduate teachers in preparation, that even though they know there's not a once place, their calculations show that there is a once place in their belief systems. So we've got some things to worry about when it comes to fractions and decimals, and we've got to help them understand it. So one more error, just one more error. 3/10 as a decimal. Well, you got to do something with that 0. So I guess we put that 0 in there, right? You got it. So other ones in there, just the simple ones from Tim Burst in groups. What happens when students start seeing 3/5 as a decimal, or 3/10 as a decimal, or 2 5/10 as a decimal? Well, look at the work that the students did. They're simply just doing division. They're trying to make numbers not end up between 0 and 1, right? Because in the counting strategies, numbers, you start at 1. if you don't count correctly, like we've done in our work together, if you count from 0 to start with, you know that there's some numbers in between. You at least are set up for it. But if you start counting by 1, maybe you're not prepped on it. So, in his words, dividing the denominator by the numerator, right? That's just something that they think is supposed to happen. So let's get on to this. What are we going to do about it? Brad, you've given us a ton of these errors, but we already knew those, right? We didn't know the data and the research behind it, but we knew those. Well, let's dive into it. Let's try a little bit of what we're going to do here to help model for the students, help them understand it, at least at the core level. Start with decimals. So I'm working with a child who's had a really strong place value background. And this number comes up. And right, 2 and 4300ths, or 2.43, right, if you don't know your place value. So we modeled it for the students, and then the books actually didn't have the right statement in there. And like a fool, I read it out, and I said, how many ones are in this number? And most students said, of course, what did they say? Right? 2. And how many tenths are in that number? And they pointed, and they said, well, there's 4 in the 10th spot. Then how many hundredths are in that number? And there's 3. Well, the student who had a really strong background looked at me really confused and said, no, it doesn't say what number is in that place. It says how many ones are in that number. And the answer are there are 2 and 4300ths ones in that number. The tenths, there are 24 and 3/10 tenths in that number, right? 24 and 3/10 times tenths would be 2 and 4300ths. And then the student goes, how many hundredths are in there? Well, gosh, there's 243 hundredths in there. So, of course, I'm sitting there going, oh my gosh, I love it. The student is able to look at these models over here when we work off these interpretations and know what to do with it. If you're used to whole numbers, you're thinking that says 243. But when you work with decimals, you can change the values of these. Now, I don't have the 3-dimensional one for this group, so we use the flats here and we call them 1. So that's 1, 2. And then we put a little decimal point down here and we call that 4/10, and that would be 300ths. So how many hundredths would there be of these little units? There's 243 of them. How many tenths would there be? 10, right? 20, 24, and 3/10 tenths. And how many ones are in here? Well, there's more than 2. I've got 2 and 43 hundredths ones are in that number. I thought it was very, very clever of the child. By the way, a good rabble-rouser. You knew I loved it. So how do most teachers represent decimals to students? Well, one thing they do is they use money. Great idea, right? You can even do exchanges with them. We had a race to 100 game earlier. You can do the race to the 100 game with them. Pictorial models to make sure they understand it, and we'll work on those here as well. If you understand the metric system, which the student earlier worked with a metric system, right, that helps. Matching up to fractions, and of course, like we talked about, base 10 blocks. Lots of different ways to help a student understand the context of a decimal. So what do we use again? Well, we got some other ones in here, and there's some ways to do this, and this is for fractions and decimals. But for fractions, you can use the same things. You can connect them up, right, with fraction circles. You can use pattern blocks, which they're pretty limited, but they have a start of a concept. You just gotta quickly wrap it up. But to do this, you also have to have good pictorial diagrams in here, and like I said, money is a great way to start with. So for you, if you feel like pausing it, use these representations with your students and see if they can put these in order. That makes a lot of sense for a student trying to make sense of decimals. So if you remember the race to 1 game or a race to 100, we had a race to 100 game earlier we talked about, where students roll a die to figure out how much they can go, and they go back and forth. Well, you can do the same thing with decimals. So use base 10 blocks, you set up a place value chart. They start out, and let's say like this, the dice roll here says 4. So student 1 would put down 4 hundredths and say, I have 4 hundredths. The next student rolls, let's say they get 10. So they have to put down 1/10. They now say, I have 1/10 and 4 hundredths, or 14 hundredths. Then the next student rolls a dice and they go back and forth until the first one lands at 1 or over 1. Now, again, this is not so much as a game as it is forced practice on saying your place value. But let's talk about some ways to do computation once this place value part is understood.
One of the many reasons that students struggle with decimals is a lack of understanding of place value. When that's the case, consider some sort of size proportional manipulative. In this case I have base 10 blocks, but there's other ways. We've glued Cheerios to tongue depressors and done other ways in the past, but this is just one approach. Now, as opposed to what you might be using with whole numbers, this is no longer 100. We're going to call this 1. We're going to call this 1/10. And it wouldn't show up on the marker, but these are going to be 100th. So when you're introducing these, you're going to introduce this as 1 and 3/10 500ths. Another way to say that, 1 and 35 hundredths. So again, this is a great start to do this, and you're going to use similar procedures in showing computation of decimals that you would have whole number. So I'm just going to do one example, and I'm going to mix in integer operations for it. So I'll clear this off, and I'm going to go through one, and I'm going to show 35 hundredths minus, let's start out with 12 hundredths. So how do we do this? Well, we start out with 35 hundredths, and I'm going to subtract 12 hundredths. So I represent each one of those numbers here concretely, but I've got to make sure that I get more detailed than that, because when I'm doing subtraction, I've got to make sure that the student understands I've got a positive number here, and I've got a negative. That's subtraction. So in this case, I also want to stretch it out a bit, because I am going to be very specific on my place value and using decomposition. So in using decomposition, 35 hundredths is 3/10 and 5 hundredths. Where if I'm trying to subtract, such as 12 hundredths here, I'm subtracting 1/10 and 2 hundredths. So in this case, when I'm going through subtraction, let's do our traditional, we like to go right to left. So the student says, okay, what is 5 hundredths minus 2 hundredths? Well, these are going in the opposite directions on a number line, so I'll take out 2 from each group. What am I left with here? Positive 3 hundredths. Let's take a look at this then. I have 3/10 minus 1/10. Opposite directions, so what am I doing? 1/10 minus 1/10, that would be 0/10. And the subtraction, it means nothing there. So what's my answer? My answer is 23 hundredths. So what did we do in this case? Well, we did, right? 5 hundredths minus 2 hundredths, that would be 3 hundredths. We then said 3/10 minus 1/10, and that would be 2/10. That's where we came up with 23 hundredths. Now, there's several different ways to do the subtraction method of it, where you're regrouping to make the subtraction come out the positive answers. But I'm going to do one just a little bit different, just for the sake of trying to get the integers involved here. And instead of saying I'm going to do 35 hundredths, let's go through the same way, but let's make it with 35 hundredths minus, let's make this now 18 hundredths. So what I'm going to do, 35 hundredths, I set it up the same way. I've got 35 hundredths, and I'm now going to subtract 18 hundredths. So let my fat little fingers try to manipulate this correctly here. Alright, so I grab through, and I'm trying to sabotage as best I can. I see 4 and 4, that would be 18. Alright, so instead of going from right to left, I'm going to go from left to right in this case. So I'm still going to attack it the same way. These are opposite directions here. I've got 3/10 minus 1/10. So what's 1/10 minus 1/10? Well, that would be 0/10 there. So I'll get this aside. No longer helpful. Now, instead of doing the normal, what you're used to saying is you can't take 8 from 5, when of course you can. It'd be negative. Well, we're going to show that here, and we're going to do that now. So what's 5 hundredths minus 8 hundredths? Well, I say they're going the opposite direction on a number line. Now, a student who's counting would probably have to match them up 1-to-1 with correspondence. But I would hope that they could just grab 5 from each group and remove them separately. So what am I left with here? Oh, that doesn't matter anymore. So what am I left with here? I'm left with 2/10 minus 3/100. Now, one way to do that would be to exchange it, but if you have a student who understands some of the proportional arrangements here, you can stack this up and say, what's my difference here? I have 1/10 and I have 7/100 here. That would mean that my answer is 17/100. So let me explain what we just did here at the abstract level. We went from left to right here. We said, what is 3/10 minus 1/10? And we said the answer would be 2/10, and we said it was a positive. We then said, what is 5/100 minus 8/100? And what was our answer? Negative 3/100. So when we subtracted here, what is 3/100 less than 20/100? It would be 17/100. So this is not a bad method if the student's having a visual discrimination issue of being able to know how to subtract or how to regroup, or they have a manipulative issue where their fingers just simply can't do all that manipulation. This is a way to help them get to the abstract level and to get the integers at the same time.
So what we just saw was an introduction to a CRA piece. And in that video, there's lots of different things that were coming out in there, right? We discussed expanded notation, even though I didn't fully write it down. We could have certainly written it as expanded notation. We showed some integer work in there, and we certainly got the decimal computation started in there. To do that, if you've ever used CRA, you know the steps. You start out with manipulative objects. You then can work towards pictorial representations. And finally, you got to make sure the abstract is understood. If you ever teach through CRA, you plan by the abstract procedure first. Make sure your procedures make sense and make sure they're based on concept. Then task analyze, make sure those procedures are the most efficient approaches. That's when you go back and find a good concrete and pictorial that will lead to it. If you want to see some more, University of Central Florida's got a couple on their MathVids website, and there's a couple other groups out there that have a lot of good information on what to do with it. And I certainly know there's some YouTube pieces on it. This is an example that we put out there in the Building Number Sense book for CRA. You can see the steps here. Let's start out with the right one. We start out with abstract. And so it's 26/100 plus 18/100. So we have 2/10. This is expanded notation, right? Like maybe I should have done that earlier, but that's okay. You know what I meant. I have 2/10, 6/100, 1/10, 8/100. What's 2/10 plus 1/10? 3/10. What's 6/100 plus 8/100? 14/100. What am I going to do now? I'm going to add 3/10 and 14/100 and find out it's 44/100. Well, if those are the steps I want, here's a concrete manipulation way to get to it. And the exact same procedural steps work with it for pictorial. When you teach CRA, you use the same language consistent from concrete to pictorial to abstract. To help get those kids from concrete to abstract, the hard jump in there, it's the language piece that really takes them through. One more CRA, because we didn't discuss multiplication of fractions. Here's an array model. And I'll walk through it fairly quickly because we've hinted at this before. But when I do an array model, 4 and 3/10 times 2 and 4/10. So see how we set this up? I've got 4 ones and 3/10 times 2 ones and 4/10. So you set them up, you organize it in this manner, and the answer is going to be a rectangle down here. So the x times the y. What's 4 ones times 2 ones? 4 ones times 2 ones. Again, 4 times 2 is 8. The answer is in ones. All right, what is 3/10 times 2 ones? 3/10 times 2 ones. Again, 3 times 2 is 6. Ones times tenths is tenths. How about 4 ones times 4/10? Well, 4 times 4 is 16. Ones times tenths is tenths. And what is 3/10 times 4/10? 3 times 4 is 12. Tenths times tenths is hundredths. Now, you might want to not say that to your best friend, as you're going to probably spit on them with it. Because, right, spit on your hand, not your friend. But the matter is, it's all language based. So when I'm doing this, the language would be ones times ones is ones. There are 8 ones. And I go through each one of these. Tenths times ones is tenths. So there's 6 tenths here. Ones times tenths is tenths. There's 16 more. And then tenths times tenths is hundredths. The answer is 12 hundredths. Then you simply add them up. So that's the concrete level. I'm using a lot of language because it's CRA, so a lot of language at the abstract level to get them through these steps. Then what do? Well, you transition into a pictorial model so that the student says 4 ones times 2 ones is, right, 8 ones. 3 tenths times 2 ones is 6 tenths. 4 ones times 4 tenths is 16 tenths. 3 tenths times 4 tenths is 12 hundredths. And like we said earlier, you add them up. So the pictorial is not to the size proportion that the concrete was, because you're trying to get them used to a pattern of language. And you're trying to get them to that abstract. And it's not like I'm going to write my 4s and 4 3/10. I'm not writing my 4 10 times larger than my 3/10. So I've got to get them past the size proportional into an abstract understanding. So they can look at this problem and say, 4 times 2 is 8. The answer is in ones. 2 times 3/10. 2 times 3 is 6. The answer is in tenths. 4 times 4 tenths. 4 times 4 is 16. The answer is in tenths, right? 16 tenths is 1 and 6 tenths. And then I've got 4 tenths times 3 tenths. 4 times 3 is 12. The answer is in hundredths. And again, we have the same approach throughout it, the same language through CRA. That way, when some students can be at abstract, while other students are still working at the concrete level, but the conceptual and procedural work remains the same. There's another one that the Regional Ed Lab of the Southeast did. So when you're working decimals, if you're looking through that going, boy, Brad, that's a bit much. I need to go a little bit slower. Here's a little more intervention side to this. Set them up to make sure that the student knows what is 1/10 times 7 tenths. So you go back to the array model, but it's going to be more at an individual counting pictorial level, and we'll try to do a little bit better with that repeated addition piece to it. But you take it out and you frame this so that in a piece of graph paper, they shade in 1/10. You then identify, I'm looking for 7 tenths. So 7 tenths times 1/10. What's the answer going to be? You got it, 7 out of that whole 100. The answer, 7 hundredths. So if the last one was 7 hundredths, what would 7 tenths times 5 tenths be? So same thing, we have our area. We're showing 5 tenths. And so what's 7 tenths of that 5 tenths going to be? So we grid it out and we shade in 7 tenths of it. The answer, I've got 35 hundredths. So I write down 35 hundredths. 7 tenths times 5 tenths. 7 times 5 is 35. Tenths times tenths is hundredths. This is one of the intervention groups we're working on here. And this was a great example. And this student was really, really sharp. So she did the same thing with fractions that we just showed. This is the expansion of it. She takes 2/4, and then she multiplies it times 2 fifths. Then, of course, like every kid in the world, she took, right, this is a large array board, right? You buy them at any hardware store. And so, of course, she has to shade in all the increment lines. I love that, and to make sure that every ordinate shown in there. So she's got it all gridded out. And then she says, okay, what's 2 times 2? And then she goes, oh, it's not a rectangle yet. So she shades in this one. You can see her work up here, 2/5 times 2/4 is equal to 4/20. But let me show you what she did here. She then grabs these blocks over here. Let's try with a little key with LD. She puts a block here, block here, block here, block here. And she turns to me, because I was sitting right behind her with the camera, and she goes, now wait, you said that in division, things don't go away or get smaller. They just get kind of looked at differently. And they have to be the same size. I say, yeah, that was with whole numbers. Do you see something here? So she grabs this block and puts it here. She grabs this block and puts it here. She then says, I see 1/5, 1/5, 1/5, and 1/5. Is 4/20 the same as 1/5? Love it. I mean, just fantastic work. This comes actually from my own daughter on the right here, where she's actually doing this as her homework now with fractions. My point would be, don't just use it for fractions, use it for decimals as well. So we covered through about half of it, and we have a little bit of time left, so I want to make sure that I get through some of this here. But I got to give you that gift. Look at it. Look at the cart or the cartoon. They're acting out. What's 2 plus 1? And he turns to his friend, and his friend gives him a sign for 3, but it looks like an okay 3. So 2 plus 1, what does it equal? Let's see it. Okay. So he says, oh, got it. The answer? Okay. Gotta love kids. All right. So there is a practice guide on this. If you want more information on what to do for helping students learn fractions, take a look at the IES practice guide on fractions. We're going to focus on number 2 right now, helping students recognize that, right, it's not always part of a whole. Fractions are simply numbers, and they expand a number system beyond whole numbers. An old researcher I used to work with once said, how many numbers are between 0 and 5? And of course me, I'm very basic. I'm 1, 2, 3, 4. I got 4. And he goes, okay, how many numbers are between 0 and 1? And we're all like, oh, right? And there's an infinite number. He goes, yeah, that's the point. Put numbers on a number line system. And that's what number 2 is here. So, first step that I'm going to do with this, and we use fraction strips. Don't call them by one, call them by whole. Put kids together and have them chart out and organize their fraction strips so that they can compare the sizes of fractions, that magnitude of them. So one of the examples we have here is you see what one whole is, and a student takes the next strip underneath it, and they're going through and they fold it in half and they label each one half. The next one goes through and tries to take a fraction strip and folds them into fifths, which by the way is very hard to do. And then further on, another student works hard and folds them into tenths. They're never this clean. That's why I had to do an electronic version of it. But what you're trying to do with this one is not get perfectly clean computation and estimation. You're trying to help them understand the concept of 1 versus 1/2. So the procedure is to make sure they understand that halves go in 2 different lengths. And if there are 2, that means there are 2 different lengths in between and only 1 separation. What often happens is a child sees the 2 in the denominator and they fold it twice. They see fifths and they fold it 1, 2, 3, 4, 5 times. By using the fraction strips or any length-based model, they're going to recognize it's 5 equal-sized movements to make the whole. And then if you got to see on the bottom, now we can start asking questions. Which one's greater, half or fifths? What does it look like when I say a fifth of a tenth? And start seeing what they can come up with. Well, if we can do this with fractions, we can do this with decimals. Once you've gone through fraction strips, take a try at decimal strips. The decimal strips allow the same approach. So now instead of 1/2, we can talk about why is 5/10 the same length as 1/2. Now we can start making some comparisons. If you like to talk about relevance, if you're a musician, you've already done this, right? You understand notes. So and they're not called 1 notes, they're called whole notes and half notes and quarter notes and eighth notes. Take those and work them in. If you have measurement, if you have someone who's very handy, if you have a construction worker, let them come in and explain how important it is to understand your fractions. And again, they're working out these length-based models, the same thing that we're trying to work on here. One of the ones I've done in the past is I stretch out a fraction, I stretch out a clothesline and we're going to use it for fractions. And you take some increments or you take some indicators and you indicate where's the 0 and the 1 is. For some students, I can indicate where 1/2 is, but most of the time when I ask them to label 1/2, they go right to the middle anyway, no matter what these numbers are at the side. So if you have a number other than 0 to 1, if you're going like -1 to 2, you probably need to label where some of the increments are. But in this case, you give some students some cards with fractions on them, and they have to come up and put them in order. And listen to the negotiation. If you got to start out with the fraction strips, the small slips of paper, hopefully they'll be able to understand that 1/4 is to the left of 1/3. Because it takes, 4 movements to get across here. Where thirds, it takes 3 movements to get across, which means a third is a larger step than a 4th step. So this allows a different conversation with students. So a student who may be confused that 4ths are bigger than thirds, they get to walk through it. I did this once at a workshop, and a teacher got very, very nervous in front and didn't remember where 3/5 was. So what did we do? We walked through fifths. Of course, we protected her. We said that, she was trying to play the kid who struggles, and we appreciated it. But then we walked through fifths, and we made sure we had 5 equal-sized steps. Then we got back to the start, and we took 3 of those steps. Then she turned and said, this is where 3/5 is located. But again, working through these kind of these fractional clotheslines based on fraction strips really helps a student understand what to do with a fraction on a number line, because we need that number line concept to be understood. So like I wrote in here, start out with some good benchmarks. Don't throw wild things at them like sevenths and ninths. Give them some ones they can work with, and then start building up. Also, I recommend here, do not send them all out as a class as a whole. It just becomes an argument. Put small groups together. Do not send them out individually. They've got no one to compare to. Let the conversation start based on some background information you taught them. Well, if we can do that on the number line with fractions, once they get that, it's time to start varying. We don't have to just have fractions in this clothesline. We can start having other ways to do this too. So, in the next slide here, we took an extension on it and we asked them to put down some of the decimals. And it made sense for them, the decimals. In fact, in some cases, it made more sense. But again, we had to have the conversation that 25 hundredths is to the left of 4/10. And of course, you know me, I'm asking questions like, but wait a second, 25 is bigger than 4. And I'm letting my students explain it back to me. And then, of course, the 5 hundredths. But that looks like a big number. Why is it all the way to the left? And so then, of course, the students are explaining it back to me. Now, you can keep expanding off of that and then having them combine to understand that there's multiple ways to represent the same point on a number line, where 2/5 is the same as 4/10. So having this kind of conversation allows students to start comparing, right? What is 75% of the whole? Well, that's where 75% of the whole would go. But again, these kind of clothesline activities really help a student understand the conceptualization of fraction, decimals, ratios, and percents. Well, expansions of it, you got it. If you don't want to have them just walk it out, you can put fraction strips right on their desk and let them do comparisons. If you know that that's where fifths are, let's break those increments into smaller increments and see what we get. My gosh, if they're all equally sized, now we're talking about tenths. And it's fun when you work with tenths as a fraction because it matches the conversation for decimal, right? 6/10 written one way, it looks different when I write it this way, but I'm saying the exact same thing. So it's fun when a kid makes that connection that fractions and decimals really, it's just a different way to write the same number. I had one kid come to me a couple weeks back and goes, why don't we just write them all as decimals? And of course I said, but I like fractions. He goes, but I don't. But at least he understood the comparison between decimals and fractions. Working with a couple students here. Instead of saying 2/3 times 1/2, I want them to say, what is 2/3 of 1/2? So to do that, I've got to start out with, okay, I need 2/3 of 1/2, so I better start out labeling where is 1/2. Then I need to identify where the thirds are between the half increment and label what is 2/3 of the way there. When I do that, I really got 2/3 of 1/2 is, you can see in the length here, 2/6. But again, breaking up that length helps the student walk through it. So rather than the kid just saying, well, 2 times 1 is 2 and 3 times 2 is 6, the answer is 2/6. I know low achievers can do that if they know how to multiply. I need them to understand that the number did not get bigger. So in this case, I got to play a little bit too, and I said, hey, by the way, 2/6, it could also be labeled as 1/3, and let the student explain back to me why. Same thing. I'm so used to kid check and invert and multiply, and I know you'll do it too, but I was doing a webinar overseas, so the time frame was off, and I think my youngest was in 2nd grade, and she was at the window of the office, and she goes, tell me what you were doing, right? So I'm lying down in bed with her late at night, and I said, well, here's what we're doing online. And I didn't say what is 3/4 divided by 1/2. I re-explained it. I said, how many halves go into 3/4? So we're looking at her ceiling, and I said, here's 3/4, and here's half. How many of those halves of your ceiling would fit into 3/4? And she goes, I don't know, about 1.5 of them. Make sense? Again, now we're starting to have a little bit more clear understanding of what we're doing. Rather than just invert and multiply, they can get through some smart procedures on this. And what's a nice way to do this? If you've ever done this before, you can take 3/4 divided by 1/2. Instead, just convert this to fourths. So it'd be 3/4 divided by 2/4 with the equivalent fraction. 4 divided by 4 is 1. 3 divided by 2 is 3/2. So anyway, now I'm just getting excited. So let's talk about some of the intervention aspects real quick before I show you one of my favorite approaches to this. One, number lines have conceptual and procedural memory attached to them. They also have a little bit of a CRA component to it that, if you notice, right, we can always go back to the concrete and work our way back through it. There is an approximation that happens with number sense from it, so you can reteach magnitude or teach it for the first time. It gets early to more difficult as you build through number lines. And like I said, those physical manipulations are so powerful for certain students. Finally, decide whether or not you want increments written in or open number lines. We're starting to see some better data come out of this. Start students out with increments, but as they move on, you can get to more open number lines for them. So let me show you some integer computations that come with it, with some number lines in there. And that Rackard, he's going crazy with that abacus. You go, buddy. Take a look at this one. I decided to have a really fun integer computation on it. What's 13 minus 34? Well, in this case, we're so used to trying to jam everything on the one number line, I mixed them up. I put a tens number line and I put a ones number line. And the tens number line, start out with 110, and I go back, and I know you don't have to do the hopping part. I like them straight bar, but you can go back and go 10, 20, 30. The answer, it's on negative 20. And then what's going to be 3 minus 4 for the ones? I go 3, and I go 1, 2, 3, 4. And I know that negative 1. So I go from negative 20 minus 1. What's the answer? Negative 21. So if you've ever done telling time or working through things that instead of going through an expanded notation, you can use number lines to show expanded notation or decomposition and do them on separate number lines per place value. This is a field model, and I love a field model. So a field model is a great way of trying to explain it if you have that, those mixed signs in there. For this one, I've got 2 plus a negative 6. And again, you're trying to say, well, you're adding, right? If instead of subtraction, I know some textbooks will change it from subtraction to adding the opposite or adding a negative. If students are having a hard time with that and they don't know what to do with two signs next to each other, help them explain what's really happening here so you can have a single direction on a number line show. So in this case, I love today, I'm starting with 2 and I'm going back 6. But a field model helps them understand what to do with the movement on a number line with one sign. So in this case, I put it together. So I say, okay, I'm either adding or subtracting 6. What am I doing here? So I give the options. I'm either adding or subtracting. What does it say I'm doing? I am subtracting. So I circle subtraction and I get rid of the addition. So what is it? It's really 2 minus 6. So in the number line, you start at 2 and you go back 6 to get negative 4. So in a field model, if this was subtracting a negative, you'd put a positive and a negative here, and what would it say? It would say I am not subtracting. So you would take out the subtraction and leave the addition. What a field model does, it helps the students see when two signs are next to each other, it helps them see what's really happening here. So again, there are ways that I've seen this done before. I've seen this done where a good thing happens to a good person, it's a good thing. Good thing happens to a bad person, it's a bad thing. I don't know if I like that one. A bad thing happens to a good person, it's a bad thing. And a bad thing happening to a bad person, it's a good thing, right? It's the morally compromised principle. Don't do that. Use the actual addition, subtraction signs, let them walk through the process. We talked about this one earlier. Make sure they can see the negatives that come through it. We're so used to doing it down here and regrouping. But you can also take integers and subtract through. So I've got 3 tens minus 1 10 be 2 tens. 3 ones minus 8 ones, that would be negative 5. What's the answer? What's 20 minus 5? The answer is 15. Well, if they don't understand integers, you kind of have to regroup and borrow. But if they get integers, it's one less step. All right, last part here, and I know we're down to only about 5 minutes left, so it's a quick introduction to my favorite part, The good news is if you look up YouTube Witzel fractions, I think you get to see more of it. I've had enough teachers and committee groups try to copy me on it. But I want to make sure I walk you through a couple steps here. First part, you can do a lot of different things. We can do multiplication division with this model, addition subtraction with this model, equivalent, simplification, and I put it down here. I do a lot of work directly on this if you ever want to see more. But let me walk through a couple examples. I'm going to start out with what makes sense. First, look at these. What happens here? Student sees this top one here of 3x squared minus 4y divided by 3x. What do students typically do? Right? Well, somehow they end up with 1x minus 4y divided by 1. What do they do? How did they get there? Right? Well, you know what they did? They said the 3x's cancel, and you're left with one set of x. Right? Because the 3's cancel out. At least in this kid's case, he got rid of one of the x's. But what's the problem? It should be here. That 3x in the denominator actually owns everything in the numerator. It shares its wealth. It's base 3x. So we've got to teach this early. That starts out with something a little smarter when we're going through any type of decomposition and you're taking 15/4. Rather than just grabbing 15/4, separate it out, decompose it for them. I decompose it to something that would be easily divided by 4, 12 plus 3, and then reteach them 15/4. There's a reason why it isn't just canceling this out. It isn't the answer 3 plus 3. The answer is not 6. The answer is 3 and 3/4. So what can I do? Where can I start them out? Well, one, choose an easy manipulative. Popsicle sticks, integer chips, something that's nice and easy they can count with. Take a look at 8 halves. So I set them up and I put this is a proportional way to approach it. So we're setting up by proportions. That's actually how fractions are written. They're written by proportions. So I put 8 over 2. And then let them reorganize based on the denominator. What am I left with? 2 halves, plus 2 halves, plus 2 halves, plus 2 halves. The answer? 4. How about 8/3? Set them up, group together by thirds. 3/3 plus 3/3 plus 2/3. The answer? 2 and 2/3. Or 13/4, right? Grouping together by that denominator because it owns everything. You end up with 4/4 plus 4/4 plus 4/4 plus 1/4. And in that decomposition, they realize the answer is 4/4 is 1 plus 1 plus 1 plus 1/4. It's 3 and 1/4. But it becomes a counting grouping activity to help them see how that ends up working. So let's talk about this equivalent fractions. We're so used to trying to set this up and making this complex, but a student who's really weak in their computation may struggle. So this is an intervention for them. I'm going to set it up the same proportional approach. I've got 2 popsicle sticks over 3, and I say I've got 2/3. So I want an equivalent fraction. Another numerator, another denominator. Now what do I have? I've got 4/6. Okay, let's do it again. Another numerator, another denominator. What do I have now? I have 6/9. So again, when you fold a fraction strip, it just keeps doubling. You really don't get the next equivalent fraction. But in this case, you're using repeated addition to help them understand how equivalent fractions work. And I give you a warning down here. You're not adding 2/3 every single time you put those more popsicle sticks in. You're putting another numerator, another denominator. So let's use that in the process here. I set it up as 1/3 minus 2/3. So I check, what am I doing? I'm adding or subtracting. Is my denominator set? Yes, they're in thirds. So you would physically move the positive and negative signs up, right? Put little cards with them on there and move those signs up. And then, are they going the equal or opposite direction on a number line? Opposite. So you take one away from each. And what am I left with? You got it. -1/3. Now listen, I know this is real quick and that you'll want to play this back. That's okay. Or watch those YouTube videos. But again, you're walking the same steps you would normally through an abstract level. You're just letting the concrete force the interaction. Let's finish up with a more complex one here. 2/3 plus 1/2. I asked it earlier, are my denominators the same? Because I'm prepping them when they're not. So what's happening here? Well, I'm adding. Okay. Are the denominators the same? No. So let's get some equivalent fractions. So another numerator, another denominator. Now I've got thirds and fourths. Nope, not yet. Go to the other fraction. Another numerator, another denominator. What do I have now? Now I have sixths down here. And I have fourths. Still not. Another numerator, another denominator. Now I have sixths. So what do? Now that they're both the same denominator, I move the signs up. We say they're addition signs or positives. They're going the same direction. So the answer, 4 plus 3. 4, 5, 6, 7. The answer, 7/6. And if you group it like we did earlier, you'll see it's really 1 and 1/6. So, but this is an approach that has really helped a lot of students through. And like I said much earlier on, we're getting replication studies from the original research that this has been a powerful intervention, particularly for students who struggle with their computation. Now, just as quick little reminders, you can take the same approach we just did and build it in with decimals. So I'm working with hundredths and tenths, and then you're going to work with hundredths and hundredths and explain how the process still works. That 40 hundredths is the same as 4 tenths. And you can do the same approach with them, right? Same direction on the number line. Now, when you're doing CRA, I do a warning. You're going to have to prep it. Small numbers first, focus on the process, and make sure that they're not using popsicle sticks all over the place. When this was sent to me, I just cried in my bed. There's a better way to do this approach. Be planful. You don't need 21st when you're working with popsicle sticks. You should have done halves and thirds. Once they understood the process, get rid of those popsicle sticks, start drawing things, and then get to that abstract level. If you're ever going to try CRA, you can pause here. We give you the CRA math strategy, and you can go through how do I set this up for myself. So here's what we did today. We talked about frequent errors, modeling decimals, fractions and decimals, integer computation, and finally, we did the multisensory math. Now, I know I'm at -2 minutes, right? I get my integers in there. But today I knew would be a super busy day, so I appreciate the extra 2 minutes on this. If you're a pausing person, make sure you press pause and talk about 3 new things you learned, or 3 things that reinforce what you did. Then think, what are 2 things I can do with these? And then finally, if you have more questions, don't hesitate to ask. But I thank you for this very busy hour, and I hope that you walked away with a lot of new strategies. Again, if you ever need to contact me, though, please don't hesitate.
Thank you so much, Dr. Witzel, for the strategies and information you shared. That was fabulous. We are grateful for the learning and look forward to future sessions. The following slides list the dates and topics that will be covered in the remaining 3 webinars, as well as my contact information should anyone have additional questions. I will type the event evaluation link into the chat box, and it will be sent to the email address you listed in your registration. Following the end of the slideshow, Dr. Witzel will take questions. Please type any additional questions you may have in the chat box, and we will answer as many as we can in the time remaining. And thank you to all of you for taking the time to participate in this webinar, and we hope you will be able to join us for the rest of the series.
Once again, here are the dates and times of the remaining webinars in the series that Dr. Witzel will present. Here are some additional resources for intensive intervention and mathematics disabilities. This webinar series and the associated materials were developed under a grant from the Colorado Department of Education. The content does not necessarily represent the policy of the U.S. Department of Education, and you should not assume endorsement by the federal government. Please feel free to contact me at any time with additional questions, and also consider checking out the CDE SLD website for additional professional learning opportunities and resources. Thank you again for joining us, and have a wonderful evening.